So if M is a closed d-dimensional Riemannian manifold, such that we have an upper bound on the volumes of one balls on the universal cover, so such that let's say the volume of each one ball in the universal cover, which I denote by M tilde, bounded by a constant V1. Then we obtain a bound for the simplicial volume. Then the simplicial volume of M, simplicial volume, and I will elaborate on what this invariant is. So I will not assume that you know what the simplicial volume is, but this invariant is bounded by an explicit constant times the volume. So 16 to the e factorial square times this constant V1 times the volume. So this is the theorem that I want to talk about today, and somehow has a history. So let me write down Larry Guth, who proved a version of that for hyperbolic manifolds in 2011. And then together with Sabine Braun, we proved the general version of that, but with an inexplicit constant. So just with inexplicit constant depending on D and V1. And then finally, Hannah Alpert proved the explicit constants here. And I will say a bit more about the history in 1 second. But let me start by explaining this simplicial volume a little bit. So the simplicial volume, kind of a strange invariant if you've never seen it before. It's defined by the norm on the singular chain complex. So we have a L1 norm on the singular chain of a space. And it's the singular chains with real coefficients. And the norm is just if you have such a linear combination of simplices. So these are real numbers, these are singular simplices, then the norm, the obvious L1 norm. And then if you have a norm on the singular chain complex, you obtain an induced norm on the singular homology by taking the infimal representative in a homology class. So induced norm, but it could be a semi-norm. So it could be that you have norm 0, because you take an infimum, although the class is not 0. So let me just say by taking the infimal chain in the homology class. That's the definition. And now the simplicial volume of a manifold is obtained by taking this norm of the fundamental class. So simplicial volume is defined by taking, so let's say we denote this norm also by this double brackets, and it's the norm of the fundamental class. And let's assume the manifold is orientable. And so this is the integral homology class, obviously. But okay, we view it as a real class in the real homology and then take its norm. And okay, there are many things to say about the simplicial volume. Let me keep it short, present you a few facts. So fact one, which is a very easy one, is there is a multiplicativity with respect to finite covers. So if you have, let's say, degree k finite cover, then the simplicial volume of this cover is k times the one of m, which is easy to see because if you map the fundamental class to this, you get to this place, you get k times fundamental class. So each representative here gives you a representative of k times the fundamental class. That gives you one inequality between the two, but you can also lift classes for a cover that gives you the other inequality. So it's quite immediate to see that we have this multiplicativity. And it immediately gives you that if you have a space that covers itself in a non-trivial way, then the simplicial volume vanishes. So in particular for a torus, by looking at the self-cover or any self-cover, you get that the simplicial volume is 0. So it's really a semi-norm. So that's one thing. The second fact, which is not as easy as this one, and not obvious at all, is Gromov's mapping theorem. And this says that, I mean, it doesn't say it literally, but it somehow says this is all about the fundamental group in some sense. So if you look at the map from your manifold to the classifying space, so the classifying map from M to the fundamental, the classifying space of its fundamental group. So you could notify V pi 1M. And always have this map, which is one connected. And this includes an isometry. In the real homology, I should say. So this is the group homology, of course, of pi 1M. And so you can map the fundamental class over there and read off the norm there. Since we're talking about semi-norms, isometry does not mean isomorphism, right? It doesn't even mean projective, but if the simplicial volume of M is positive, then in particular, the fundamental class cannot map to 0. So in particular, if the simplicial volume is positive, the manifold is rationally essential. So positive, then and rationally essential just means that somehow this injective in rational or real homology. Yeah.
Just one question about this theorem. Maybe I'm stupid there, but there are no conditions on the manifold. So if you scale
the simplicial volume 0.
Yeah, but if you scale the metric, wouldn't you then get that the right side becomes very small? Because the volume becomes smaller for the balls in the volume of M.
But it goes in there's a tension in different direction. Yeah.
I see.
Yeah. Yeah.
So this is what
yeah.
This replaces the Polish conditions.
Yeah.
Okay.
Exactly. I will say something. It is a kind of coarse or macroscopic version of scalar curvature, the condition, which is yes.
Now, if you one ball, you scale the metric, it becomes larger and the volume becomes lower.
Right,
so
right. So they act against each other.
Yeah. Sorry.
Yeah, no, that's an excellent question. Just that. Okay, there is a third fact that I want to either remind you or tell you, probably have heard about it, which is that it's very hard to compute this invariant in a precise way. But there are a few cases. And one case is hyperbolic manifolds. So the Gromov first straightening method gives you that the total volume of a hyperbolic, so let's say d-dimensional, this just means d-dimensional hyperbolic manifold closed is the Riemannian volume of the hyperbolic metric divided by universal constant Vd, and okay, one also knows what Vd is. Vd is the maximal volume of a geodesic simplex in hyperbolic space. So it is proportional to the Riemannian volume. And actually, we do prove this theorem for hyperbolic manifolds. This is also the way he stated it. He compared the hyperbolic metric to an arbitrary Riemannian metric under, well, a certain condition, which is you want to think of as a kind of scalar curvature condition. All right, and then also, that already starts somehow a little bit the history of this theorem. Let me put this, okay, let's say remark. So if you put on your manifold a lower Ricci curvature bound, that actually implies such a universal bound on the one balls of the universal cover. You say something like Ricci curvature is bounded by from below by -1. Then this theorem was known since the 80s because this is Gromov's main inequality that he proved in volume and bounded cohomology. So let me not write down the theorem again, but let me just say under a lower Ricci curvature condition, the above theorem is Gromov's main inequality. About the commercial point. All right. Now, yeah, let me now come back to your question, because you can understand the theorem and is understood as a version of the main inequality for macroscopic scalar curvature. Let me write. Can be understood as a macroscopic scalar curvature analog. And I think probably in this seminar was discussed before quite a few times. If you look at the characterization of scalar curvature in the asymptotic expansion, then somehow the lower scalar curvature bound means like the upper bound for the volume of infinitesimal balls around points. So if you put here as condition a bound on the one balls in universal cover and somehow going between M and M tilde in terms of curvature shouldn't play a difference, right? It's kind of the philosophy. If you put a bound, an upper bound on the one balls of the universal cover, this is like or should correspond to a macroscopic analog of putting a lower scalar curvature bound on your manifold. This is kind of the analogy. And it's not much deeper than that, maybe. It's a wonderful analogy, but in the end, we will work just with volume when you prove things and not talk about macroscopic scalar curvature. But that's kind of how you should understand this analogy and why it's an evolvement from Gromov's main inequality. So let me put this here, lower scalar curvature bound corresponds to upper bound on putting like here infinitesimal balls on balls, but somehow how small the radius is you should choose depends on the point. And the concept of lower macroscopic curvature bound. Maybe if we're talking about one balls, you should maybe say at scale 1 would correspond to upper bound on the volume of 1 volts. And somehow conveniently you take the 1 volts in the universal cover. You do avoid things like, I don't know, 1 volt is already the whole manifold or things like that. So it makes sense to do this on the universal cover.
If you talk about manifolds, and we formulate the theorem for more general spaces, you just need a volume, right?
Yeah.
And fundamental classes.
Well, that's the point. So first of all, you have to talk about a specific homology class, and somehow there's a very distinguished class for a manifold.
Mm-hmm.
Okay, there is a concept like pseudo-manifold, right? Where you still have a class you can talk about, but it's not a manifold. And I think, so I don't know, but there might be a chance because somehow I haven't talked about the proofs yet. I mean, if you follow Guth's proofs, and this is the proof that we developed further with Sabine Braun, that's really a manifold proof. But somehow the proof by Hannah Alpert rests on developments that came a little later and which apply to non-manifolds. So I don't know, but I think there is a chance. And yeah, let me say something about the history somehow. Different contributions. So as I mentioned, Guth in 2011 proved this theorem for hyperbolic manifolds. But I will, when I tell about the proof idea a little bit, I will tell you that he doesn't really use much about hyperbolic manifolds. He uses some very general properties. For example, he uses something like the fundamental proofs residually finite.
Actually, how bad or good is the invariant Gromov computers with VD?
Yeah.
And then you have the faculty squared V1. Can one compare these invariants? When you have hyperbolic manifolds, you have certainly a value for V1, I guess.
Yeah.
So how bad is 16 times D faculty?
So I forgot what
I think VD
know about this.
D faculty also. Asymptotic.
Yeah. Does anybody know? Yeah.
I think I remember it was in quotation by.
Yeah, I think by so-called.
So very
we don't have we have, I think in dimension like 3 and 4 there is a very precise computation of this. But in higher dimension we have certainly an asymptotic.
But Hagerup and Munkholm, I think, has figured out some asymptotics there.
Hagerup.
Hagerup and Munkholm. Yeah. Okay.
Okay, then in this proof, okay, I will tell you later maybe about the proof idea. Then with Sabine, okay, let me say one thing right away. The technique that is used, it's the nerve method. The widely used method in this context where you construct covers by balls on your manifold and you use the simplicial complex given by the nerve to say things about topological invariance. The ingenuity, of course, lies in how do you construct the right covers given the geometric condition. That this is where the ingenuity lies. And this is somehow quite difficult, or it was a very novel contribution here. With Sabine in 31, we built on the nerve method and we're able to prove the theorem in general, but with inexplicit constant. Proved general theorem with inexplicit constant. So just constant depending on E and V form. Also using the nerve method, building on Guth's proof. And then Hannah Alpert these are publication links. Provided the explicit, maybe actually speculated a little bit about how to get the explicit constants, but couldn't do it. And he provided the explicit constants using a different method, using the minimal hypersurf method, using minimal hypersurface method. And let me write down some names and then I will comment on this. Tomovich, Ishak, Nabokowski, Rothman, and Macroscopic are the names I want to mention here. So what is this? There is this minimal hypersurface method. It started with Shun-Yao in questions of positive scalar curvature. And I think Guth adapted it first in general to the macroscopic context. And then it didn't happen in this paper, but a few years later, Guth was studying the case of the theorem where V1 is almost zero, so very small. So there is an addendum to this theorem. If V1 becomes too small, then Guth showed if V1 becomes too small, then the manifold has the bounded d minus one dimensional unison bit, actually bounded by one or two. We'll not define it now, just, yeah. And he showed that, but the proof was really about manifolds. And then in this work, this was generalized and I think also made more explicit in constants for in non-manifold context. And Papasoglou provided a simplification, a very metric geometry proof, which is quite simple, and which allows somehow it's much more easier to extract from this method explicit constants. And so this was just in the case somehow when V0 is almost zero, but somehow Hannah Alpert figured out how to adapt these methods and combine it with methods that we have in our paper to actually compute explicit constants. So that's somehow the history of this theorem. And now I want to tell you a little bit about the general structure that Guth used in his proof. So let me want to keep that.
So when you mentioned the minimal hypersurface method here, then so we have the usual problem with the singularities in higher dimensions or higher codimensions. Is this also present here, or is this
right? So this
more robust than this?
Is a very robust version of that, which is like a metric geometry version. So when I say hypersurface, it's not really a hypersurface. You should think of this hypersurface like the codimension one, almost tree-like structure sitting in your manifold.
Mm-hmm.
So it's not a submanifold, or not necessarily a submanifold. Actually, it will never be in this context. And of course, you are also never interested in infinitesimal notions like curvature. It's always about there are constants involved, and it's about volume. So it's a very robust version. You don't run into this issue. Yeah.
Okay.
But it can still be made explicit. So this is the wonderful thing about this method. But now I want to talk about the first method, about Guth's proof. And I said, somehow the geometric ingenuity lies in how do you construct the cover, right? This is somehow where the geometry actually lies somehow. And I will almost disregard this in this talk because I will focus on something that you might know much less. And this is what I want to focus on. So let's jump in. And I write here hyperbolic, but I will tell you in a moment that it's actually much, much less than hyperbolic that Larry Guth uses here. Let's call gamma the fundamental curve of the manifold. And closed hyperbolic manifold now, d-dimensional. And one thing that it uses about this specific situation is that the fundamental group is residually finite. So this means it possesses a residual chain of subgroups so you have gamma starting with gamma, you have gamma 1, gamma 2, and so on, such that each gamma I is not just a subgroup, it's also normal in gamma, and it is of finite index. And if you intersect all these subgroups, you only get the neutral element, so that in some sense it converges to 1. This is a property of these linear groups, like hyperbolic groups. And some of the relevance here is, of course, by covering theory, corresponding to these gamma i's, you get finite covers. Right? Such that M, this finite cover corresponds to gamma I. And in such a residual chain, somehow the system of these manifolds goes to infinity. And that's somehow what you want. So this is the minimal length of a non-contractible loop. And it happens that these become bigger along such a residual chain. So what Guth does is he has to do something where he has a large enough system, somehow like a homotopy version of a large injectivity radius. So whatever he does on a large finite cover. And by the first fact about simplicial volume, we know it's multiplicative. So if you understand the simplicial volume of the cover, understand, we know what the simplicial volume of the base manifold is. The other thing that he uses about hyperbolic manifolds is that they are spherical. So the universal cover is contractible. And actually, although he doesn't state it, if you read the proof of Guth, it really works for closed spherical manifolds whose fundamental group is residually finite. So he could have stated this as a condition. This is what he means about hyperbolic. And the other thing why he uses hyperbolic is because he doesn't state it in terms of simplicial volume, he states it in terms of the volume. But actually, I mean, this is what he does. And then, okay, so how do you proceed? So you take an I, which is large enough so that this is, I wrote down at least 6. So take I large enough such that I think 6 enough. And then you see here, so what he does is, and this is somehow the hard part now, and I make life easy for myself by saying construct a suitable, using the geometric conditions, construct a suitable covering by balls on MI. And I will not say how he constructs the cover, but let me say which cover you could do. I told you that if you impose stronger condition, lower Ricci curvature bound, it's a stronger condition by the Bishop-Gromov inequality, gives you such an upper bound on the volume of one balls. So if you're in the situation that you have a lower Ricci curvature bounds, it's quite easy to say which cover ring by balls you could take. Let me just say in this case, and use this as a reproof of the main inequality if you want. So for main inequality, take any covering by, let's say, one balls or 3 balls actually. It doesn't matter. Wait, 3 balls such that the concentric 1 balls form a maximal packing of the manifold. Packing means they're disjointly sitting inside the manifold. So that thing would work if you have a lower Ricci curvature bound. In this situation, it's much more complicated, and somehow the covering by balls is by balls of quite different radii. They don't have the same radii in the case of Guth's theorem. But this is what he does, and then kind of the standard feature, then you have always a map, the nerve map, to the simplicial complex given by the nerve of this covering, let's call it U. So there is somehow you want to map the centers of the balls to the corresponding vertices, and somehow you can always extend this almost canonical way. That's the nerve map. So you look at this map, and in general, it's quite useless to use any topological consequences for MI, but in our situation where the systole is big enough and MI is a circle, this suffices to construct a homotopy retract. So there is a map back such that this composition is the identity. So let's say homotopy commutative, homotopy retract. And this is because the systole is big. 6, it should be enough. And the other thing is the higher homotopy groups of MI are 0 or K bigger than 2, because the manifold is hyperbolic, in particular spherical. Because somehow you construct this map by an induction of the skeleton, well, you know where to map points, edges, but as soon as you want to extend it to the two skeleton, you somehow have triangles in here that you want to fill. And you want to make sure that the triangles are small enough to say, oh, the systole is big, so we can fill the triangle. And then you proceed to the higher skeleton, but then there is no topological obstruction anymore because the manifold is filled. So it's a standard way, and you get this homotopy retract. Then there is another step where Guth really has to invest quite a lot of work, which is you cannot estimate the size of this nerve. It might be very big. It might have many, many simplicities. But what he shows is, let me call the nerve map F maybe. What he shows is that this map F is homotopy. Actually, homotopy. Okay. I mean, let's simplify a little bit. Even what he shows is that F is homotopic to F prime such that the d-simplicities in the image of this F prime is bounded by a universal constant. I'm always referring to this statement here, right? Times the volume of MI.
And the nerve of U, so this, is this a metric object? It's not, right? It's just a simplicial complex constructed out of the overlapping pattern.
So I don't, yeah. Yes and no. So it is a metric object in the sense that, and you should regard it as a metric object. For example, if you have the standard simplicial nerve, you would put standard Euclidean metric on a simplex and then extend it to a path metric. And you want to use that in this step because you have to homotope the map down and you want to use things like, okay, if the volume or locally the volume is small, it cannot cover the whole simplex, which means I can somehow push it down and things like that. So you have to argue, this is a geometric step. And this is actually a non-trivial, really non-trivial step. And I'm also disregarding some subtleties. So this is not the standard nerve construction, which is somehow, the standard nerve construction is fine in this situation where all the balls have the same radius. Because what you want here is somehow that the geometry of this nerve somehow takes into account different radii. So you have something that's called rectangular nerve construction, which takes this into account. So somehow you have, yeah, it's a bit more involved, but it's important to also look at this map as like a map, geometric map. And somehow the difference or the difficulty in Guth's proof is that in comparison to this proof, in this situation, this map has a Lipschitz constant, which is universally bounded in terms of somehow the Ricci curvature lower bound. And because it has this uniform Lipschitz constant, also tells you then what happens to volume. In Guth's situation, this map, I mean, I guess it's unclear whether the Lipschitz constant can be bounded, but cannot be bounded a priori in any easy sense. So what he shows is that on a large volume part, it can be bounded. And it can go crazy on a very small volume part. And somehow this balances out in such a way that he can still somehow get the right volume estimates or images of simplices, can homotopy things down, can somehow bound the number of simplices in terms of the image of the, in terms of the volume of the image and things like that. So it's, yeah, it's really quite involved. But as soon as you have that, then you're in business, because now you have a map, I mean, the identity map on M1, on MI, and this is homotopic, this identity is homotopic to a map that factors over simplicial space whose number of E-simplices is bounded like that. Now, just track what's happening to the fundamental class, right? We take fundamental class, since it is homotopic to the identity. If I go around that, then I get a fundamental class. But if I factor over a simplicial complex whose E-simplices are bounded in number, then it's clear that I have a representative of MI whose number of E-simplices can be bounded by this estimate. So actually what Guth gets from this is he gets it bound. And let me put that here. So the definition of simplicial volume was about taking the L1 norm on the real chains. You could do something naive and just take integer chains. Of course, then it's never zero, the simplicial volume defined in these integral terms. But you could do it, right? It's just somehow the infimum of the L1 norms of the integral representative of the fundamental class. But actually, you get a bound for this by this method. And then you know that the volume of MI is the volume of M times the degree of the covering. The degree of the cover is the index of this finite index subgroup. Bring it on the other side. Okay, maybe I do it in 2 steps now. All right, and you get the following: the ordinary simplicial volume, which is multiplicative, so we could write it like this. And this is certainly smaller than this integral version, which is the quantity that is actually bounded by Guth's method. And this is then smaller than this. So. The general structure modulo, of course, very important question, how do you construct this cover in the general situation? Okay, so what Guth really does is, for large i's, he bounds this quantity, not just the simplicial volume. And this raises, I think, some interesting question, or opens another context to this whole story, which I want to talk about. But okay, so if you have questions about the proof, maybe now it's a good time, because now I will somehow take this observation that actually something stronger is proved to go into a little bit different direction. Yeah.
So since the nerve was constructed, roughly speaking, from the centers of the balls in the covering,
Yes,
and then I guess the cycle representing the fundamental class that we're using for the simplicial volume is an image of a subcomplex of the nerve now.
right. Yeah, yeah. I mean, you move the fundamental class to the right side, and you know in the singular chain complex of the nerve can be written as a sum of this many simplices, the top dimensional simplices. Yeah.
Yes. So then is there a way to see roughly what this efficient representation of the fundamental class is in terms of where the centers of the balls are?
No, no, because somehow where you lose complete control over this is when you go back. So this map, I mean, this map is quite geometric if you follow the proof, right? Still complicated, but still somehow geometric. But this map is really constructed in this homotopy way. So I don't have a good geometric control over the map back. And somehow to express the fundamental cycle, I would understand this. And here, I mean, here I still have things like a Lipschitz control, at least on a large volume subset. Here I don't make any assumption, and I don't think I can actually.
This like coming from the Whitehead theorem or something like
I wouldn't say Whitehead theorem. I mean, you do it somehow simplex by simplex, so skeleton by skeleton. You always extend to the next skeleton, and somehow the first obstacle that you run into, I mean, somehow if you have points, you map it to the center of the box. So that is clear. And then also on edges, you just could connect them via geodesic. Then to extend it to the two skeleton, you have these triangles here, the geodesics between center of balls, and you want to make sure that the triangles are small, so you can apply this and fill the triangle somehow. But then it becomes kind of murky. I mean, then you don't have any topological structures anymore because you can always fill simplicial spheres by simplicial disks in extending to the next skeleton. But somehow geometric control, I think, becomes hard to track. So
it's somehow related to the efficiency of representing elements of the homotopy group.
Yes. And these things are also studied, right? Yeah.
Thank you.
Maybe another question. So you count the number of d-simplists in the image, and then you argue that the chain representing the fundamental class in the image is a combination of those where the coefficient is 0, 1, or -1.
No, you have to somehow, in the proof, you also control the coefficient. That I just did not say, but the proof gives you control of the coefficients, not just of the number of simplices. Yeah.
Okay, that is built in.
That's built in, yeah.
So it seems to be important to have this map back from the nerve to MI, for which you're using that.
For which we are using the asphericity.
Exactly. Right, and the vanishing of higher homotopy groups. But before we learned that the simplicial volume, maybe it's better to regard it as an object that lives on the classifying space of Taiwan. So this seems to be the universal receptive block.
Exactly.
Where this thing lives. Is there a hope that one can kind of reformulate?
So somehow when you extend Guth's theorem to what we did to the general case, you have to drop residual finiteness and you have to drop the asphericity. So residual finiteness is somehow the more complicated issue, and I will tell you a bit more, but maybe I can, since you asked, say right away, if you have just the issue of asphericity, instead of going back, you could go to the classifying space, right? I guess now you should maybe take the gamma I. Sorry. Actually, I mean, what you want is something like this. You would like to go here, or maybe M or MI. Actually, the way we do it is we do everything in the end of the universal cover. But somehow, in theory, you want, instead of going back, you want to go just further to the classifying space and then apply the mapping theorem by Gromov, which says that you can track the norm of the fundamental class by going over there. And since you know you factor over something which is small, then you're done. So that is actually, to drop the asphericity is relatively easy. Yeah, that's the mapping theorem.
Okay.
Yeah.
All right. We should also ask if someone in the Zoom is interested in asking questions or encourage people. But you can ask anyway. At any time.
Yeah, everybody can ask at any time. So, okay, if not, then I want to go slightly off, but actually it only seems like we're going in a different direction. Actually, it will help for the proof in understanding how to drop the residual finiteness. But somehow I want to go in a slightly off direction, starting from this observation. You actually can look at this, right? You could also take something like the limit of those, so the lim sup over I going to infinity, and take this as a kind of a new invariant. And then this method, at least in the spherical residual finite case, gives you an upper bound on this invariant by the volume. And this is important if you want to somehow get a version of that theorem for homological invariant. So here is an easy exercise. I won't do it. It's not that easy. No, it's relatively easy about concurrent duality. Which is the Betti number. So we'll write mi now. Yeah, okay, let's write mi. I mean, but it's for general closed manifold. The Betti number is bounded by this integral version of the simplicial volume. If you can bound somehow the norm of an integral representative of the fundamental class, you can bound all the Betti numbers. You don't even need any. It's true like that. It's an exercise. Now here we're looking at such a quotient over a residual chain, and there is a theorem of Luck that says if you do something similar for the Betti numbers, you get an invariant which is called L to Betti number, which I will not define in this talk. If you want, you can take the theorem as a definition, but of course it's not the definition, because it would only be a definition for residually finite fundamental groups, and it's an invariant that's defined in by generality. But nevertheless, in this situation that we're in, this theorem tells you that this is the limit of the corresponding ordinary Betti numbers normalized by the degree of the coloring, which is just the index of this finite index subgroup. Now, the theorem can be continued now to get a bound on this L to Betti number. Okay, so theorem always refers to the first theorem, right? So theorem continued. And here you don't have anything like the mapping theorem for the L to Betti numbers. So here we really need a spherical. You don't need residual finiteness. This is something that we proved with Sabine. But in the case that your manifold is a spherical and residually finite, Guth's proof, in addition with this observation and Wolfgang's theorem, gives you a bound on the L to Betti numbers. So if M is, and I refer to the setup here, is in addition is spherical, and as in the theorem, then the L to Betti numbers in any degree of your manifold can be bounded by, actually you have to, for the general case, you have to make the invariant a little bit worse. Let me just write CdV1, but it can also be made explicit in the work of Hannah, times the volume. And again, putting all these things together, you see the proof already in Guth's paper, at least for residually finite fundamental groups. But residually finiteness can be dropped, and you have a general statement like this. Now, actually, this invariant, I like this invariant quite a lot, because and this is more an aside, this is not needed somehow for the general theorem, but maybe it is interesting to know that we could, of course, ask whether there is a kind of Luck approximation, so this is usually called approximation theorem, whether there is a Luck approximation for the simplicial volume by its integral variant. Maybe, yeah. So there is, of course, a trivial approximation theorem of the simplicial volume by its ordinary form, because it's multiplicative, the simplicial volume. But if you take here the integral statement, then you get an interesting question. And here's a theorem that Guglielmo, Laleux, Cristina Papianchini, and myself. Which says in a very particular case there is such an approximation theorem. So for a closed hyperbolic free manifold, and any residual chain in the fundamental group, so let's call it gamma again, the fundamental group, you have that the ordinary simplicial volume is the limit of I goes to infinity of this integral variant of the simplicial volume divided by the index of the cover. This is a very specific theorem for hyperbolic free manifolds. It is incorrect for four-dimensional hyperbolic manifolds or higher, but there is still a kind of universal constants that estimate the two invariants. And
I have a sort of maybe more basic question. So you now are stressing the integral simplicial volume,
right,
compared to the actual simplicial volume.
Right.
So I mean, naively one might think that one is kind of, if you think of the universal coefficient theorem, maybe same thing. So why is it different at all?
It's not true for. I mean, for example, as I told you, I mean, this is, in general, the simplicial volume comes from a semi-norm. So the simplicial volume can be zero, like for the torus, right? I mean, this integral thing is never zero. So it's really kind of very naive invariant. It's much closer to somehow estimating what's the size of a minimal triangulation of your manifold, rather than looking at, although it's also not, this is not literally true what I said, but it's somehow in spirit, it's closer to estimating the size of a minimal triangulation rather than looking at the most efficient cycle of the fundamental class, which could involve cycles which are completely wild and somehow.
Maybe S1 is good if you run around S1 n times. You can divide by n.
Right.
And then if it's zero, you can't divide by n.
It's a little counterintuitive since, I mean, when you define homology or the fundamental class, then you do it in integral homology anyway.
That's true. That's true.
And now we have a big difference.
Yeah, but again, if you talk about norms, you usually have a vector space, right? And not an integral group, just an abelian group.
And I also have a second question. This concerns this constant, which was already brought up before.
Yes.
Question of Wolfgang Lück, namely, I mean, okay, so we have this Hannah Alpert result. Is this constant in any way expected to be the optimal one, or is this?
It's just no.
And what would be the optimal? Because before we saw a possible link between this constant VD in this for the hyperbolic case.
The VD is much smaller than the.
And this should give. Is this? Does it make sense to expect that the VD is the correct constant here as well?
So isn't there? I mean, you're much more an expert than I am in this. But somehow, if you go back to Guth's theorem, which was formulated for hyperbolic manifolds, right? It says that it's still there actually. So this is essentially the hyperbolic volume, and it says the hyperbolic volume is bounded above by some constant times the volume. And isn't there conjecture, maybe also, I think Schön-Yao maybe, in scalar curvature, somehow if you have on hyperbolic manifolds that somehow if you kind of a comparison statement about scalar curvature. If the scalar curvature of an arbitrary metric is somehow bigger or equal than the scalar curvature metric of the hyperbolic metric, then the hyperbolic volume is at most the volume of this arbitrary metric. There is some conjecture about this, right? Some comparison conjecture. I mean, I'm looking at the experts that are more experts than I am in this. But this is somehow a conjectural statement, but then you have to formulate it in terms of the scalar curvature. I think if you formulate in this macroscopic scalar curvature context, I don't think we have a candidate for like the optimal constants. Yeah.
Remember, so this constant Vd, which is not on the blackboard anymore.
Yeah.
Is it linear? So what is this constant?
This is no, it's not linear. It's the maximal hyperbolic volume of a geodesic simplex. I mean, it is the volume of an ideal regular simplex.
How does that?
It has an explanation. I think the paper by Gromov and Moon,
right,
give an explanation for it for all dimensions.
Yeah,
it's certainly into it. I forgot how this works.
I'm sorry, I forgot. I cannot. But nevertheless, even if I could remember, I mean, this is not somehow our guess what the optimal constant. I don't think we have a guess for the optimal constant. And but again, there is something if you put like very specific hyperbolic manifolds, scalar curvature condition, then there is a conjectural.
So what strikes me a little bit, so in this systolic inequality, we do have a much better constant, which is linear in the
right, which is actually to your work, right? But that I mentioned about the so I don't think the original proof gives you that, but we have a very good constant. Yeah. I mean, luckily we now have a constant due to this set of techniques. Yeah, but I'm pretty sure this is not the optimal constant. There are various steps in the proof where it's.
One question on this form, you see that the limit on the right side is independent of the chain. Does one know this in general?
No,
it's
but it's related to a set of questions in a completely different context. Actually, very much related to, if you know, this fixed price problem around cost.
Yeah.
This is a kind of this is the fixed price conjecture for this integral simplicial volume, that this actually does not depend on the chain. Yeah. But we don't know it. And we don't know it. It would be, I mean, in this case, we know it. But in general, we don't. All right. Yes, sure.
You gave this interpretation of a simplicial volume being something like counting the number of simplices in the best triangulation, in the smallest number of simplices in the triangulation. Was that more the real simplicial volume or the integral simplicial volume? Do they both have the same interpretation?
So I said I said that if you take this integral simplicial volume, it is not true in a literal sense that this is measuring the minimal number of triangulation, because you can still allow a very large simplices, singular simplices in the definition of that. But I said something like it feels more it's in the spirit of this rather than the ordinary real simplicial volume. So don't take this as a literal statement, right? I mean, there are people more in combinatorics who actually study what they call complexity. They're actually looking at the number of minimal simplices and triangulation. And there's actually a very recent PhD work, which I know because I'm in the advisory committee, by Federica Bertolotti. She's a student of Roberto Frigerio, who proved that in the context of hyperbolic, now I'm not completely sure whether it was free manifolds or she needs higher dimensions, but at least in the context of hyperbolic manifolds, also asymptotically, it makes a difference whether you consider the integral version of simplicial volume or this notion of minimal number in a triangulation. So it's actually hard to prove that they are different also asymptotically, but she could prove. So it's a different notion. But yeah. Maybe I shouldn't even have said it, but all right. So now I would proceed and tell you about how to drop residual finiteness. Because residual finiteness in group theory, very often we're happy with that condition. But somehow in a geometric context, it's very hard to impose geometric conditions on a manifold that ensures residual finiteness of the manifold. Actually, the only condition that comes to my mind now is like saying this is the fundamental group of a locally symmetric space. And maybe there are a few other like constructions. I mean, you could take connected sums or something like that. But it's very hard to put geometric conditions that ensure this. So somehow you want really to drop this condition on residual finiteness. And and somehow I want to present you now a variation of the simplicial volume. It's actually, in some form, it's a variation of both this side and this side, which is actually the right object to work with in this context. It's a bit, you've never seen it, a surprising context. So gamma again will be my fundamental group. And the setup that I look at is now that it's acting on a Cantor set. So let's say this is a degree. It's actually a continuous action. This is the setup I'm looking at, but it also comes with a probability measure, this Cantor set. And the action should be measure preserving. But somehow this situation I'm looking at, kind of surprising maybe, but given such an action, you can define an invariant, which is a generalization of that invariant here and also of that. So I need maybe a bit space here. You said with discussion of 90 minutes?
Yeah.
Okay. Start here. So we want to define a variation of simplicial volume. So we start in the top homology of our manifold. But we start with set coefficients. So this is where our fundamental class is living. Now I want to rewrite this homology in a slightly more complicated way. So this is the homology of the singular chain complex. But instead I'm taking the singular chain complex of the universal cover and somehow have the fundamental group acting on this. I tensor over the group ring of gamma. And here I have the trivial model of the group, which somehow basically just is like dividing out, and this is the singular canonical isomorphic to the singular chain complex of M itself. But I want to write it in this complicated fashion, because now I can define a map. Let's call it I star, comes from the inclusion of Z as constant functions into a space of continuous functions on my Cantor set. So, okay, this is maybe unfortunate similarity of notation. So this is continuous functions, integral value, not singular chain complex. And I have gamma acting on this because gamma acts on X. So I have this complicated looking thing And you know equivariant homology, you could also write it as this is the equivariant homology of M tilde with coefficients in this harmonic. And this chain complex here, it has a norm. It has a norm itself, namely, if I have a sum, and a typical sum is like you have functions here, tensor simplex, and then the norm, let's index it like this. I mean, let's say norm in quotation marks, because everything is just appealing groups. So for a norm you want to scale, you cannot do that here, but never mind. You can define something like this, and you just take the kind of L1 norm on this function space. And this is where you use the measure. Okay, you just integrate somehow the absolute values of these functions. And this gives you kind of norm on this chain complex. And then if you go to the homology, you can always take the minimal representative. So you get a norm or semi-norm on this thing. And now you can take the fundamental class, you move it over there and take its norm. It's a new invariant of the fundamental class. And it's called the integral foliated simplicial volume. Kind of a long name. So it's the norm of somehow, I suppose it's mapped by star. I push forward the fundamental class. Again, this map here is inclusion of constant functions. And you get an invariant, the integral foliated simplicial volume. This invariant is potentially bigger than the ordinary simplicial volume. Because if you have a nice, efficient representative in this chain complex, you could always integrate this. Right? There's always a map here by integrating the coefficients, and you land in, again, the homology of this, but now with real coefficients. Because if you integrate such a function, even if it's integral value, you get a real value. So if you have an efficient representative, integrate there, you get an efficient representative of the fundamental class in the real singular chain complex. Therefore, this will always be potentially bigger than the ordinary simplicial volume. And if you do this whole definition with real valued functions, you really get just the ordinary simplicial volume. So you could define, let me not write it down again because I think it's clear. You take everything, everywhere R, and this will just give you the ordinary simplicial volume. So this is nothing new, but this is potentially a new invariant. And now I admit that this, just think, maybe I put it here. This is a bit of a strange definition. I should say that this goes back. Okay, so there is a description of integral foliated simplicial. I'm not sure right now whether it was called like that, but there is a definition which looks different, but it's kind of in a similar spirit in work of Gromov, but he attributes it to Con. And it makes sense because this is kind of very close to foliated versions of simplicial volumes. I haven't seen it in writing in Con's work, but somehow this is attributed to him, but it's not in its algebraic form. Now, what's the connection to what we did before? First of all, this quantity here that you've seen in this theorem, by which you could define anytime you have a residual fundamental group, you can recover from this. And actually, it also shows you that this limit always exists. It's not clear whether it's independent of the chain, but it exists. And this is the following remark. Or fact, I won't prove it now that in our paper. So if, again, gamma is residually finite, then this thing here that we looked at before is a version of that. But now the question is for which action? What is the control set and what's the action for the following action? We take the projective limit of these finite groups. You view it as a topological object. It's actually a profinite group. If you would go over all finite index subgroups, it would be the profinite completion of your group. Here we only go over one chain, but it's a profinite group, so compact, totally disconnected group. It comes with a Haar measure, which you can normalize to be a probability measure, and gamma x by obvious translation, measure preserving. If you take this action, then this is actually the same. You recover this. And Wolfgang's question about the independence of the chain is about the independence of this notion for the specific measure preserving action. And this is actually, like, there is a corresponding question for cost. And maybe I also state this theorem by Clara. For those who know the cost, I won't define it now, but the cost of an action -1 is bounded above by this. I mean, okay, in the setup that gamma is the fundamental group of a closed manifold, otherwise it doesn't make sense. So there is a bound like that. Anyway, so let me now go back to our theorem, which is not about, which is a priori not about all this thing, but now we have this notion, which we can do for any group, because every group admits such an action. That's an easy thing to prove. So even if you're not residually finite, you can play around with different actions, and you always have this. And even if you just are interested not in L-to-Betty number, for which you need this invariant to get bounds, but you're just interested in the original theorem about simplicial volume, it's nevertheless better to work with that definition, even if they coincide in the real version. So that's somehow the right thing you want to look at. And why is that? Why is that?
Can you give a hint what kind of X one should think of? In the case that they are, say, more.
Well, I mean, one X you can play around with all with this. The Bernoulli action, where you act by shape. So take 0, 1, take the probability measure, which is 1/2 here, 1/2 here, and take this. This is one action.
And this is a reasonable one.
This is a reasonable one, yeah.
Which gives you something.
Yeah, yeah.
How can this be? I mean, this seems like a little bit like magic. It feels like magic.
Yeah, yeah.
Somewhere something must. So, where's the actual mathematics? Okay.
Okay, so yeah. So why, let me formulate it like, why the shift from on the level of chain complex, from the chain complex to this strange looking chain complex here. And somehow on the level of spaces, it's the transition from M to this space, which is many ways to think about this strange space. this mix between Cantor set and a nice continuous topology. You can think of this as a kind of foliation whose leaves are isomorphic to homeomorphic to n tilde, and the transversal of that foliation is given by x. But why, right? Why the shift to these objects? And the philosophy is somehow becomes, I mean, I can only be a bit vague now, but somehow, if you look at this situation, right? Here we put into x, when we go back to the situation of Guth's proof, he plays around with a large enough finite cover, and somehow we can express this, which is bounded by Guth, by this, and we put here all the finite covers. So in the slogan you should think of is that this space here, it involves a universal cover, but it's still a compact space. So this is a compact space, right? Because X is compact, and the gamma quotient of M tilde, which is M, is compact. A compact space, but this compact space behaves like a space with arbitrarily large system. That somehow, whenever you do, and somehow the theorem here is a truly equivariant theorem in some sense. So the version where you have B0 is very small, then the addendum, which I did not fully write, would say then the manifold is not essential. That would be its, in particular, the simplicial volume is 0. So that version you can prove somehow on the universal cover in a proper homotopy category. It's an almost non-equivariant statement. But this statement is really very much about the fundamental group, and you have to make things equivariant. And to do that, you need a large system when you construct these covers by balls in an equivariant way. And yeah, and somehow you do it on this space, which if you think of X being this here, behaves a little bit like a space with arbitrary large system. I know it's a bit vague philosophy, but it's actually
it wasn't also a trick that now, because you have the X, you can cut changes and put them in other way together to get smaller estimates. I think you remember of the PhD thesis of
yeah,
Marco, right?
Yeah.
You have now more freedom to do something, because originally you were in the constant functions. Now you can also make manipulations in the X direction.
Yeah, you run into this thing, for example, in constructing covers. I mean, it starts with, you take one ball, right? And now very often you want to somehow, in the situation of the main theorem, there I described you the cover by balls. It's just covered by 3 balls, such that the concentric 1 balls form a maximal pattern. So how do you construct this in an equivariant way? You take a 1 ball and you want that all its translates are disjoint. That's the minimal thing, right? Just for 1 ball, you want this. But this is already something like, oh, okay, the system should be at least 1. So you need this to realize that. Now, in this setting, if you do this on X times n tilde, it's much easier to realize this equivariant if you replace balls by compact open subsets in the Cantor set times a ball, because you can always shrink this compact open subset arbitrarily and then achieve that there are no self-intersections of this one orbit. So in that sense, it behaves like you work on a compact space and it nevertheless has arbitrary large system. That's somehow the trick. And okay, let me maybe finish now in the last few minutes. And okay, let me very brief. So what you do to attach Guth's proof is that you construct an equivariant family. And I have to say what I mean by equivariant, of covers by balls, or coverings, I'm never sure, covering balls. So let's call it the cover. And the family is indexed by this contour set X. So for each point in my contour set, I construct a covering by balls, Ux, on the universal cover. And this cover will look like a cover that Guth constructs. The additional difficulty is now to make this equivariant in the sense, and the equivariance is this. The individual Ux won't be equivariant. You will never achieve that, but the family is equivariant in that sense. So if you take the translate of this cover, then it's just the cover at the point gamma times x. And so that is what you achieve. And then somehow the difficulty to adapt this. And then you have to do everything is somehow indexed over the contour set. Everything you do. Homotoping the maps down. So you get a NURB construction also in this setting. So there is something which is called the NURB of this family. And the NURB of this family is a space that lies over X. And each fiber over some little x in big X is just the NURB of Ux. But it can be assembled to a nice topological space, and there is a NURB map. And actually, you can also map this space to X times the classifying space. And somehow you have then a similar situation in Guth's proof. You want to homotope this down so that the number of cells in the image that are hit is small, or it's bounded by this constant. Now the question is, what is the number of cells? This is actually a kind of average that you take using the measure mu again when you count cells. But you can do that, and then you can estimate in the end you actually work with this definition. But this is the same as the ordinary simplicial volume, but you can estimate this from this construction and conclude. And if your manifold is spherical, then you don't have to go to this place. You can actually then construct a homotopy refract here and get a bound on this object. And this additional piece of information gives you then a bound on the Alberti numbers, because the Alberti numbers are still bounded by that. So that is also something that is true. And right, okay. I think I stop here. Thanks.